Hi YouTube, welcome to this first video of a video series I want to do in exploring boundary value problems. So in this video we want to talk about solving some of the ordinary differential equations. So this is a background refresher kind of a thing. So we want to discuss a variation of parameters, and that will be helpful in solving PDEs later on. But first of all, just want to recap some of the concepts, the foundational concepts that we need to know before solving PDEs. And the reason for exploring this variation of parameters, which I'm highlighting right now, is because variation of parameters, there's some kind of a thought process and some solution techniques which we use to solve ODEs, which are very useful later on, especially in boundary value problems with respect to heat transfer. So just to recap, this is a video series. We want to discuss boundary value problems, especially with respect to heat transfer. Okay, so for example, convection, of course. Alright, so you should have some background already. You should know how to solve ODEs, and we should know that ODEs have a particular solution if it's a non-homogeneous ODE, and if it's a homogeneous ODE, then there'll be a homogeneous solution. And for the ODE, as a whole, for the ODE, there will be a particular part of a solution and then the homogeneous part of the solution. So today we want to explore how do we get these solutions using variation of parameters. So previously, you might have come across this method of undetermined coefficients before, where we first solve for homogeneous ODE, and then then we guess the particular solution of ODE. Alright, so if your ODE is something like this, and so continuing, we have a we know that we have for any like ODE, we usually have a particular and homogeneous solution, and we use the method of the undetermined coefficients, which is kind of a guessing of what the particular solution looks like, and that is kind of there's an educated guesswork behind that. Now, is there a more concrete way perhaps to do the solving of the particular solution? So what we want to look today is the variation of parameters. So we want to take a look at this method for this method for first order ODE first. Now this already assumes that you know how to solve the homogeneous part, and usually the homogeneous solutions will look something like this. Okay, so I'm just going to put usually homogeneous can take the form of exponentials and sines and cosines. These are the usual homogeneous solutions for ODEs. Very commonly find. Alright, so suppose we have this first order ODE, which is more simple, and then we have this kind of a function here, u prime plus kt, which is just a function of t, and let's multiply into u, and this is the homogeneous part which I'm highlighting, and this is equals to some function ft. Now normally for this kind of first order ODEs, we can consider using some sort of integration factor, and that's kind of a very roundabout-ish way, I would think. And I couldn't, for me, I didn't quite like using it because I thought it's like one more extra thing to memorize. But we want to look at variation of parameters, and maybe this is a way that's more intuitive and takes less memory. So when we do variation of parameters, we always want to solve the homogeneous part first. So step 1, solve homogeneous part. Okay, so as what we mentioned before, usually the full solution is in this form. Okay, so u of t equals to u. So this is the homogeneous solution. So I'll just multiply this into some constant c1 plus u p t times some constant c2. And whatever these constants are, it depends on the boundary conditions, of course. And yeah, it'll depend on the boundary conditions. So what this statement is saying is that you can take a linear combination of the homogeneous solution and the particular solution, which I'm highlighting respectively. Alright, and we combine them together to gain the full solution of that ODE. So this is a general thing we should already know. And yeah, first step, of course, we want to solve the homogeneous part. That is pretty straightforward. So the homogeneous part, I'm just going to highlight and copy here, and that will be equals to 0. Okay, so how do we solve it? Let's put it in a more familiar way. Du dt plus kt into u equals to 0. Now after this, we can just do a simple separation of variables. Du dt equals minus kt u. Okay, so they're subtracting ktu from both sides. Next thing you know, you can just put you can bring u to the left side. So it's du divided by u, du over u equals minus kt dt. Alright, so now we can just perform the integral. Okay, I'm just going to perform integral here. So that should be pretty simple. Then if we integrate the left hand side, then we'll get a ln of a u, and that will be equals to this integral of minus kt dt plus some constant c. Okay, and if we take exponent of both sides, so u, at least the homogeneous part, because we're just solving the homogeneous part of the equation, that will be equals to exponent of whatever this is over here. Alright, and next step, we can just take this exponent to the c down. Okay, so we'll have this times exponent to the c, and of course that is just a constant we can just call a. So I guess I'm going to put a, which is some arbitrary constant. So, and that will be equals to, yeah, the homogeneous solution will be equals to a times exponential of this, okay, where a equals exponential of whatever this c thing is. Now, given an explicit expression in k, we can solve any homogeneous first order ODE. And let's take a look at some examples. Let's say we have something like this, something that looks maybe a teeny bit scary. So t squared plus 2t plus 1 u equals 0. Okay, so what's the homogeneous part? As what we can find is that this becomes our k, so to speak. This becomes our k. Alright, so kt equals to whatever I have in this bracket here. So since we already have the homogeneous part down, I'm just going to copy this over, and since we have kt equals to whatever expression here, you can copy this expression and put it here. Now that's all we are doing. So next step is to integrate whatever this t square, this expression here. I'm going to take the minus sign out. Alright, now I'm just going to integrate the inside as per normal. Oops. I'm just going to integrate the inside. So I'm just taking the minus sign out. I'm going to integrate the inside. So I'm just going to cancel this whole thing. I'll put a bracket here. So t squared will integrate into t cubed over 3. Next one, we'll have a 2t, then we integrate it into t squared. And 1 will integrate into t. And then of course there'll be another arbitrary constant I will just call k. Alright. And now, as usual, we can take this k out to be another exponential of k, exponential of minus k in fact. And then we'll just do something like this. Let's multiply it by b. And that's usually the case. So in this case, b equals to exponential of minus k. Yeah, so probably from now onwards I'll try and speed it up by skipping a few more steps, but yeah, you already know what's going on. So we found our homogeneous solution, which is this, which we have here. Now let's say we have something that also may look scary for a first order ODE. So we have this, and this is the full thing we want to solve. Okay, so I'm going to say, let's say we have this exponential 5t. Alright, now how are you going to solve this? Well, as usual, we already assume that we have a homogeneous ODE, homogeneous part of the ODE, and this will be the particular part, or this one we will have to solve. This extra bit here means we have a particular part of the ODE. Okay. Alright, so how are we going to deal with this, so to speak? So first thing first. Let's go. Okay. We already have the homogeneous part. Okay. We have the homogeneous part, right? So how are we going to solve for the other part? Well, there is a simple math trick that we just have to remember. Simple math trick. Okay, what we assume that the particular solution of t is some function into the homogeneous solution of t. Okay, so this is very important for variation of parameters. So what we are just saying is that we can just come up with some random function vt, and we assume that this vt is going to relate this homogeneous solution to this particular solution. Now this may seem a bit iffy, especially when your homogeneous and particular solution may look nothing like each other. So let's say the homogeneous part is equals to t squared plus 2 t plus 1. And then let's say the particular part, for example, is exponential of alpha t, where alpha is just some constant. So this looks nothing at all like this, but does it still work? Well, all we have to do is just to substitute in. Okay, we just substitute in this in here into the homogeneous part, and this into the particular part. And now we can find that Vt, okay, now we can find that Vt equals to just the exponential of alpha t over this, which is the homogeneous part. So no matter how strange your homogeneous and particular solutions are, as long as we can still find a Vt, which is what we use to vary the parameters, and it will still work. Okay, so let's generalize this trick, so to speak. And this trick is what we call the variation of parameters. Okay, so let's generalize this variation of parameters. Okay, so we have some u prime here plus kt into u, and that will be equals to some particular something on the right hand side. Okay, so we already solved for the homogeneous part. Let's say we solved for UHT, and we already found out earlier what was UHT. UHT was just okay, where is it? The full one. Yeah, I think this will be sufficient. Okay, where UHT is already what we found out earlier. So if we have this KT in front here, then this will be the homogeneous solution that we have found out. Okay, so what is the particular part? UP of t. Well, using that trick we were talking about earlier, assume UH or UPT equals to some variation parameter function, whatever you call it. We call it Vt here into UH of t. Alright. Okay, so now what do we need to do? Our next step, we'll want to substitute this expression back into this which we have over here. So what can we do? We'll need to differentiate this. So u p t prime. So that's the differential. Then we'll just need to apply the chain rule here. U h t prime plus u h t into v prime t. Okay, so you can see it's going to be slightly long, and let's put it down. Let's just put it down here. Let's fit all this in, and u, okay, will just be this. Okay, so again, we are just substituting this particular solution into this, the first one, the original ODE, and we assume that we have UHT already. Okay, so we already have UHT, and all we need to find out is what this V of t is. Okay, it may look messy now, but let's just try and collect these VT terms out. Okay. Alright, I'm going to factorize the VT out. Oopsie. Yeah. I'm going to factorize the VT out. UHT prime plus K of t. And both of these we kind of already know. And then we'll have a V prime t into UHT, and that will be equals to some P of t. Okay.